Welcome, everyone. Thank you so much for joining me today. I am absolutely thrilled to welcome you to this video overview for the Cade Moore Polytechnic Institute's Physics 101 course. Today, we're jumping right in to introduce your brand new assignment, which we are calling Project Freefall. Now, here at the Institute, we firmly believe that above all else, learning should actually be fun, which is exactly why we focus this portion of our Physics 101 course on the physics of amusement park rides. Because, let's be honest, it is one thing to understand physics conceptually and just stare at formulas on a piece of paper, right? But it is an entirely other matter to actually, physically, feel the immense forces of physics pushing against your body. And this project is going to introduce you to the intense engineering behind drop tower rides. Okay, here's a quick look at our agenda for Project Freefall. 1. The thrill of the drop. 2. 3 ways to stop. 3. Your engineering challenge. And 4. Beyond the amusement park. So, let's dive right into Section 1. The thrill of the drop, gravity and safety.
I want you to just think about the sheer scale of the energy we're dealing with here. Picture a vehicle and its passengers with a combined mass of 1,000 kilograms. If you drop them from a height of, say, 40 meters, they hit a speed of about 28 meters per second. That generates a massive 392,000 joules of kinetic energy. Now, in a perfect ideal physics problem, they just keep falling. But in the real world, your job as an engineer is to safely dissipate every single joule of that energy before they hit the ground.
And the stakes literally couldn't be higher. We aren't just slowing down, we have to do it within very strict regulatory safety limits. For instance, standard STN EN 138014 dictates that maximum deceleration cannot exceed specific g-force limits, to protect the human body. Because we have seen rare but really severe, real-world incidents in the amusement industry. Things like metal fatigue that leads to snapped high-tension cables. These kinds of unfortunate events highlight exactly why precision engineering and absolute fail-proof redundant safety systems are literal matters of life and death.
Moving on to Section 2, 3 ways to stop. The braking systems. First up, we have mechanical friction brakes. This is probably what you're most familiar with. Just like a traditional drum brake, physical pads squeeze against a spinning rotor or drum. This whole mechanism converts the ride's kinetic energy directly into thermal energy, or heat. It's highly effective. But because it relies on direct physical contact, those parts are inevitably going to wear down over time, and they'll definitely require maintenance.
Now, to move away from direct friction, we enter our second category, hydraulic brakes. This system relies on Pascal's law. Discovered way back in the 1600s, this law states that pressure applied to a contained, incompressible fluid is transmitted equally in all directions. So what does this actually mean for us? It means we can take a relatively small mechanical push and multiply it into a massive clamping force. It's a real game changer.
In a hydraulic system, a specially engineered incompressible fluid acts as the messenger. When pressurized, this fluid travels through tough steel lines and flexible hoses to push pistons outward with just incredible power. Believe it or not, it's the exact same principle that stops a heavy-duty commercial truck, just applied directly to our drop tower.
Our third category is electromagnetic braking, and this one operates completely contact-free. It's governed by Lenz's law. Basically, when a conductive metal fin, which is usually attached to the falling passenger car, passes between strong permanent magnets mounted on the tower, it induces electrical currents. These are called eddy currents, and these currents create their very own magnetic field that naturally opposes the falling motion. Pretty amazing, right? The secret sauce behind this system lies in a really simple equation: force equals K times V. Basically, this means the magnetic braking force is directly proportional to the velocity of the drop. So, the faster the car falls, the harder the brakes push back. And as the car slows down, the braking force naturally and dynamically tapers off. This creates a beautifully smooth deceleration without using any friction or even any electricity.
Comparing these options reveals some really vital engineering trade-offs. Electromagnetic brakes are practically wear-free, and they act as an incredible fail-safe because they work even during a total power failure. But since their force relies on motion, they provide zero holding power when the ride is fully stopped. Hydraulic friction brakes, on the other hand, well, they require more maintenance and fluid checks, but they provide massive stopping power, and they can lock a stationary car firmly in place.
All right, Section 3, your engineering challenge, Project Freefall.
So your task as a learner at Cade Moore Polytechnic is to propose a brake design system of your choosing for a hypothetical drop tower. You need to detail exactly which mechanisms you've selected, how they'll safely dissipate those hundreds of thousands of joules of kinetic energy, and fundamentally explain why your choices are the absolute best fit for managing those physical forces, all while prioritizing passenger safety and comfort, of course.
As you're working on your design, you should strongly consider proposing a hybrid system. Real-world engineering rarely relies on a single point of failure, so perhaps you might incorporate magnetic eddy currents as your primary braking mechanism for that really smooth, contact-free deceleration. But then include hydraulic friction pads as your safety fallback, just in case that primary system fails or malfunctions, or you just need to hold the car at a complete stop at the bottom. You really got to think carefully about how your systems interact.
Moving to our final part, Section 4, Beyond the Amusement Park, Real-World Applications. The reality here is that mastering these core physical concepts, fluid dynamics for hydraulics, electromagnetism for eddy currents, and the logic of fail-safe redundancies, this stuff equips you for a really wide array of highly critical engineering careers. The math and the physics, they just don't change when you leave the theme park. Because while amusement parks absolutely need engineers and technicians to design and maintain their rides, these exact same skills are incredibly widely applicable to all sorts of fields. Whether you end up designing regenerative magnetic brakes for modern electric vehicles, or engineering landing gear for aerospace, maybe securing commercial heavy freight truck fleets, or programming complex industrial robotics, the exact same physics apply. As you'll often hear in the industry, while our Physics 101 course here at the Institute focuses on the visceral fun of roller coasters, the technology you're mastering in Project Freefall is the exact same technology that keeps the entire modern world moving and stopping safely. So, how will you harness these forces? I am just so incredibly excited to review your Project Freefall proposals and see how you tackle gravity itself. Thank you again so much for joining me for this video overview. Best of luck on your designs, and I'll see you in the next one.